Thanks for joining today. Welcoming all to our series on hydronic distribution system design. What all are the things which somebody really need to consider? Hope you have already been through my previous videos, which are talking about the constant flow system and the variable primary system. In this particular thing, we are going to discuss about the primary secondary variable system in both configurations, series and parallel of a chiller. So let's continue. This is a typical configuration of multiple chillers with multiple loads in the parallel configuration. Here you can see two chillers are there in the parallel and there are isolation walls which are provided. Here it is a constant primary and variable is an option which has been provided. So this is called the primary loop, and there is a secondary variable system. The secondary pumping system is there. The pumps are there, one working on standby or both of these pumps can work if the load is there. And multiple cooling loads. At cooling load, there is a two-way actuator valve which has been provided, two-way control valve which has been provided to control the water flow in the coil to ensure that desired comfort is going to be achieved with the water flow control. Here it is a VFD drive which has been integrated to the system. There is a common leg or a common header or a decoupler line which typically named as is being provided between primary and the secondary to ensure based on the flow requirement how the water is going to flow. Let's assume in a typical conditions in the primary and the secondary flow has to be same. Actually, if I'm talking about in the primary, if 100 GPM is the flow, in the secondary also it is expected that flow is going to be 100 only. Now let's assume a case wherein one load air handling unit is not working, which is not really required for the particular time. What will happen? The constant flow is going to be pumped at 100 GPM over here. The secondary is going to take only 50 GPM to cater to the coil load of coil A. So what will happen here? It is 100 GPM water is coming. 50 is only being taken into the secondary loop. The rest 50 GPM is going to be circulated into the primary loop to ensure that my chiller is not going to be tripped. The secondary case, it may possible when the load on the primary side or the flow on the primary side is 100 GPM, and if system is not properly balanced and designed, here it is a case wherein 110 GPM flow is required. So a return water, the hot water or the water which is coming from the system is going to be bypassed from here, which can create issues into the system. So it is the best case when both of these systems are balanced, provided 100 GPM over here, 100 GPM of the flow in the secondary side, and based on the chiller staging and the load, it is going to be managed. It is also advisable to put a flow meter in the primary as well as the secondary to ensure the proper staging of the chiller along with the cooling load. So this will avoid most of the issues which happens in the secondary variable system. So if there is a issue wherein the secondary water is going into the system, this increases the temperature over here. So let's say my chiller is designed for 7-degree outlet and 12-degree inlet. If the water which is over here is 7-degree and the return water which is coming at 12-degree, it increases the water temperature supply in the coil. So this increases the opening of the control valves, and these random opening of the control valves are called death spiral in the HVAC language. There are two options to avoid death spiral conditions. One, staging of the chillers by flow, so that the primary flow is always equal or greater than the secondary, which I had already mentioned. If it is 100 GPM, I need to ensure it is secondary also it is 100, or the primary is always on the higher side than the secondary, so I can avoid this death spiral conditions. The second, insert a check valve over here, a swing check valve, which is a low pressure drop check valve, which will ensure that water is not going to come from here and it is not going to increase the temperature of the supply water line if the system is not balanced properly, thereby increasing the flow through the operating chillers. So the flow from the operating chiller is going to be sufficient, and here the temperature gain issue is not going to be there. It is advisable, as I mentioned, provide the pressure drop, low pressure drop swing check valve over here in such conditions. Talking about the multiple chiller load conditions where we have already discussed, I had mentioned I am going to discuss about the low delta syndrome. So low delta syndrome is the temperature gain which is coming, the temperature of the return is coming low actually, and it is restricting the chiller loading actually. So if the secondary system return water temperature is lower than the design temperature, so design temperature is just 12, it does not allow chiller to load on the maximum capacity, and it creates the low delta T. It results in the greater pumping and chiller and cooling tower energy consumption because chillers are going to operate at the part load, and part load means sometimes it is at 50% also, and chiller are inefficient if it is working at 50% and 60% of the loading all the time. It is always better to operate between 80% to 100% of the flow condition and the loading conditions. It also reduces the chiller plant cooling plant capacity because the chiller is not optimally performing and not delivering the cooling load which is really required, because the load is more, but because of the unbalancing of the system, the temperature which is of return water is much lower than the design conditions. So the capacity control valves are the reason for such issues. If it is not properly designed, the flow from the capacity control valves are going to be. So today the pressure independent balancing valves are much more popular, or the energy valves which are much more popular into the market. I will make a separate video for selection of the PIBC valve or the capacity control valves. Yeah, I have already advised. For the low pressure drop conditions in the decoupler line, swing check valves are the best option to go for it and avoid such issues. The size of the bypass line from the decoupler line or the bypass line also plays a very critical role in terms of design. So it is advisable, it should not, the flow through the decoupler line should not exceed 110 to 115% of the flow from the chiller. So I need to ensure that it has been designed properly, and it can save cost also if it has been properly designed. Instead of going for a standard size of the header of supply or return, I can choose an option. I can lower down with reference to the flow requirement. The secondary, if I'm talking about if these chiller are configured into the series configuration, here you can see rest on the load side is going to remain same, but in the series there is going to be a pump for one chiller and going to be a second pump for the second chiller, and here it is going to be the system is going to pump to the load side, and it is going to be the configurable. Hope you have liked the content. It is going to benefit for your project requirement wherever you are working in. Requesting you to subscribe my channel, click on the bell button so you are updated about the new videos which are coming in. And in the next video, I will come with the distributed pumping system for the large installation. Thank you. I'm also requesting, if you do have any question about your system you wanted to discuss, I'm open. Put your comments, put your remarks in the chat box. I will come back to you on that. Thank you.